Okay, we're going to continue looking at strong acids and strong bases here, and weak acids and weak bases. Well, let's first look at the acid. I'm going to write the acid equation different. Rather than write the acid equation as an ionization, I'm going to write it as a hydrolysis reaction. As you recall, H plus, is H plus stable? No. In other words, when we say H plus, we think H3O plus, and that comes because H plus is instability. And so HCl plus H2O liquid, this is going to produce what? Acid donates, bases accept. In other words, the base is going to take the H from the acid. And so what's the acid in this case? Acid's HCl, base is water. So what's going to form is the base takes the proton, so we're going to go H3O plus plus Cl minus. That's what we end up with. Now, is there a driving force for this reaction? Let's take a look at the acid chart here. The acid chart. So is there a driving force for this reaction? So the acid going forward is this. That means the base is water. If we go backwards, what's the acid? What's the base? In other words, the base takes the H plus. Who's taking the H plus? Chloride or hydronium? Hydronium's taking an H plus from chloride? A hydrogen? Actually, chloride has no hydrogens. And so what's going to take it, if we go backwards, chloride takes an H from hydronium to form HCl, and hydronium loses an H to form water if we go backwards. And so this is the acid, this is the base. Now which one's stronger? Which was the stronger acid? HCl or hydronium? HCl. So this is stronger, this is weaker. So we have driving force there. What about the bases? Well, it turns out water is stronger, this is weaker. The bases, water is stronger, chloride's weaker. And so we have driving force here. So when we have a strong acid, we say this. Strong acids ionize or hydrolyze completely. When they ionize or hydrolyze completely, this is ionization, this is hydrolysis, they form a lot of hydronium in solution. In fact, this reaction we expect to go forward, and so a solution of HCl should consist of hydronium ions and chloride ions. And so a solution that's marked HCl should consist of hydronium ions and chloride ions in solution. That's what we expect to find. There's driving force for the formation of that. So strong acids produce a lot of hydronium, or H plus, in water. Let's look at a weak acid. This is this weak acid that we looked at earlier. Let's take another weak acid. Well, acetic acid is a pretty good weak acid. Let's just go with that. Now, when we have a weak acid, that's the ionization reaction. What's the hydrolysis reaction? Hydrolysis is just a reaction with water. And so what forms in this reaction here? The base takes the hydrogen. So this is the acid, water is the base. So if the base takes a hydrogen, what form? Hydronium. This is the conjugate acid of water. And the acid loses. If the acid loses hydronium, what are we left with? Acetate. Hydronium and acetate. Do Do we have a driving force for this? No. There's no driving force because this is a weaker acid, this is a stronger acid. This is a weaker base, this is a stronger base. We just did this one. So the driving force is this way. And so what we have is we have partial reaction. Partial reaction. This partial reaction, not much, just a little bit of reaction. In other words, they say weak bases slightly react, or they slightly ionize, or they slightly ionize, or slightly hydrolyze. And so there's a big difference. There's a big difference here. If I look at a beaker of acetic acid, in a beaker of acetic acid, what I find most are acetic acid molecules and water. And then there's going to be a very small amount of hydronium and acetate. And so it's going to be like 99% acetic acid molecules, like less than 1% hydronium and acetate. And so what happens in this is we say that this solution is strongly acidic. HCl is strongly acidic because it has lots of hydronium present. Whereas acetic acid is not strongly acidic. This is much more weakly acidic because there's not much hydronium. Hydronium is really what packs the punch in an acid solution. And therefore we can rank these. This is the table in your book, but we'll just use the table that I gave out as a handout. Therefore, we can rank these. All these acids are strong acids. These are going to ionize completely because they're all going to form hydronium, and the hydronium is weaker. But all these are not going to hydrolyze completely because they're going to form hydronium. Hydronium is stronger, so we're going from weaker to stronger when they hydrolyze. And so it depends on how much of an uphill battle it is. So all the weak acids will partially react. All the strong acids will completely react. Now, how much reaction we get depends. So for example, here, like phosphoric acid, acetic acid is really weak. Acetic acid is down here. So acetic acid is, we get like less than 1% reaction. However, with something like phosphoric acid, we get more like 25% reaction. Because phosphoric acid is a lot stronger. And so if we get 25%, we form more hydronium. And so the stronger the weak acid is, the more hydronium we form. The weaker the weak acid is, the less. And so it depends on the strength here. We're going to get partial reaction. Okay, that's going to impact the pH. The pH is a function of how much hydronium. So for example, HCl is going to have more hydronium. More hydronium means a lower pH. Acetic acid has less hydronium. Less hydronium means higher pH. So this is a higher pH, that's a lower pH. So it's going to impact the pH. Well, the pH, we'll come back to the other stuff later. And so this is going to have an impact on pH. This is going to have a higher pH. This is going to have a lower pH. Now pH is due to the amount of hydronium in water. And pure water has some hydronium in it. Pure water, let's look at this reaction. This is called self-reaction or auto reaction of water. And so we'll take a look at that here. And so let's say one of these waters is acting as the acid, one is acting as the base, or vice versa. And so the acid loses a hydrogen, the base takes it. And so this is going to form, well, it's going to form hydronium, the base takes it, and hydroxide, the acid loses it. And so going here. Now, this hydronium is what we call the conjugate acid of this base. In other words, this is the base acid pair here, and the hydroxide is also over here. In other words, if we go backwards, what's the acid? Well, the acid loses a hydrogen, the base takes a hydrogen. And so going backwards is what we have. Now, is there a driving force for this reaction? Let's compare. What's a better acid, water or hydronium? Do you need the chart for this one, or can you say with confidence? Which one is a stronger acid, water or hydronium? Hydronium. And so this is going to be weaker, this is going to be stronger. Which is a better base, water or hydroxide? Hydroxide. So this is weaker, this is stronger. And so normally we say that there is no reaction, but are all the water molecules moving at the same speed at room temperature? No, we see a distribution. What was that distribution called again? What did it look like? What was plotted on the y-axis here? Population. What was plotted on the x-axis here? Kinetic energy. And if we look at the entire population of water molecules at room temperature, are they all moving at exactly the same speed? No, there's going to be a mix of speeds and energies, kinetic energy being motion speed. And that mix is going to have a shape like this. Even at room temperature, there's going to be a very small population of high kinetic energy molecules. And then there's going to be a cutoff here. We'll call this the border. If it can exceed this energy, that's enough energy to break bonds. That's enough energy to cause a violent collision. In order for this to happen, we have to have a violent collision, correct? In order for this to happen. In order for this to happen, we need a violent collision. And it turns out that, out of 1 billion water molecules, maybe about 4 out of 1 billion will react. And so 1 billion will be out here, and then maybe there are 4 up here that have enough. Or actually, it's going to be more because it has to have a collision. Collision has to be successful, so maybe more up there. But anyway, going back to this, what that means is this. It means the driving force is reversed here, but a tiny fraction of these can roll uphill, high enough, because it's like the ball pit, and we're going to create, what do we create? A dynamic equilibrium. Obviously, hydronium and hydroxide are very reactive. They want to react immediately and go downhill to water. But you cannot stop the collisions, and the collisions are going to continue to occur here because of this population. Once in a while there's going to be an accident, but the accident leads to reaction. But this is just part of nature. Well, we can measure how much. At 25 degrees C, the hydronium ion concentration, we can measure. This is the molar. When we have square brackets like that, that's the molar concentration. Is 10 to the minus 7 molar. And the hydroxide ion concentration, because this is produced in a 1-to-1 mole ratio. So for every hydronium that's made, 1 hydroxide is made. And so the hydroxide will also be 10 to the minus 7 molar. So that. Now we have the pH. The pH is just looking at the this guy here, the 7. So this is going to be pH 7. This is the power of the hydrogen ion or hydronium ion. This would be the power of the hydroxide, POH, which would also be 7. So the pH and the POH are 7. Now an interesting thing happens here. An interesting thing that happens is that the couple of things. One, the hydronium times the hydroxide ion concentration is equal to a constant. And it's going to equal 1.0 times 10 to the minus 14 at 25 degrees C. These are at 25 degrees C, by the way. And because of the property of power functions and logs, the pH plus the POH must equal 14.00. H3O plus times OH minus 1 equals a constant. Equals 1.0 times 10 to the minus 14. So what happens is this: in pure water, the H3O plus concentration is equal to the OH minus concentration. That's pure water. In acid solutions, acids, what do? Acids make H3O plus or make OH minus? Acids make H3O plus. So in acid solutions, we're going to have more H3O plus than OH minus. And in base solutions, base will add hydroxide. And so here the hydronium is going to be less than the hydroxide. This constant is called K sub W. KW. It's the water ionization constant. Here's the reaction here. It's two waters colliding violently to form some hydronium and hydroxide, which are unstable. Here's for pure water is neutral. Neutral means the H plus and the hydroxide are equal. In acid, the H plus is greater than hydroxide. In bases, the hydroxide is greater than the acid, which are wrote over there. Determine the hydroxide ion concentration in a solution which is H plus of 10 to the minus 5 molar. If H plus is 10 to the 5 molar, or H3O plus is 10 to the minus 5 molar, we could use this equation to do it, or we could use the pH and POH to do it. Do you know what the pH of this is? 5. And therefore, the POH must be 9, because 5 plus 9 will give us 14. And therefore, the OH minus concentration must be 10 to the minus 9 molar. Or we could just do it algebraically here. So if we solve this equation for the hydroxide ion concentration, the hydroxide ion concentration is going to equal Kw, which is this constant 10 to the minus 14 divided by the H plus, which is 10 to the minus 5. And 10 to the minus 14 divided by 10 to the minus 5 gives us 10 to the minus 9. And so the hydroxide ion concentration is 10 to the minus 9 molar. And so that means the hydrogen ion concentration is bigger. That means this is an acidic solution. This is an acidic solution. We have more hydrogen ion than hydroxide. The solution is acidic. If it's not an integer, then the pH has a different equation. These are the equations we could use. I'll write them on the board. This is the pH loop. So one way, we can go from H plus to pH. If we want to calculate it mathematically, let's say, if it's kind of a weird number, 5.3 or something like that, then we use these equations. pH is equal to negative log of H plus. The H plus is 10 to the minus pH. So the pH is equal to negative log. This takes us from H plus to pH. If we want to go backwards, then we use this. This is called the anti-log here. You can interchange between H plus and hydroxide using the KW equation. And we can do the same with the hydroxide and the POH using this log and the anti-log, the pH and the POH using that equation there. So these are the equations. You don't have to memorize these equations. We give it to you. What are the pH, POH, and hydroxide and H plus? 0.01 molar sodium hydroxide. So if we do 0.01 molar sodium hydroxide, well, that means that we have 0.01 molar. This is strong electrolyte, so we're going to have 0.01 molar hydroxide. 0.01 molar hydroxide is equal to 1 times 10 to the minus 2 molar hydroxide. And therefore the POH is equal to 2. POH is equal to 2. And it's going to be 2.0. This is the coefficient here. The coefficient is 1, but we can do it like this. If the POH is 2, what is the pH? 12. And that means the hydrogen ion concentration must be equal to 10 to the minus 12 molar, as if the power of the hydrogen ion. The power of the hydrogen ion has to be 12. It's actually the negative power. We have to put that negative sign in there. They didn't, you know what, they didn't do the sig figs. I'm not going to do it either. This is, officially this is sig figs for the power functions. Follow a set of rules. I'm not going to talk about the rules. I'm going to skip them. What are the typical pHs run about? Well, the pHs are going to run typically from 0 to 14, or it could be less than 0 and greater than 14 as well. But this is your standard range here. And if we have pHs from 0 to about 4, it's strongly acidic. That would be 10 to the 0. 10 to the 0 would be 1 molar H plus. 1 molar H plus is strongly acidic. Down to 10 to the minus 4. 10 to the minus 4 would be 0.001 molar. 0.001 molar is still considered strongly acidic, even though it's pretty dilute, isn't it? 0.0001 molar. Seems to be pretty dilute. And then pHs from about 4 to 8 are weakly acidic. If it's less than 7, weakly basic. If it's greater than 7, well, 4 to, let's say, not 4 to 10. 7's about neutral, so anything around 7 is neutral. It's balanced. Strongly basic would be up to 14. So pH of 0, strongly acidic. pH of 14, strongly basic. And 7, right in the middle, is neutral. What are some examples of strongly acidic? Well, strongly acidic examples would be like battery acid. That'd be pH 0. Stomach acid is around pH 1. Lemon juice is around pH 2. Vinegar is between 2 and 3. Wine is between 3 and 4. Tomatoes are about 4, slightly acidic. Coffee is pretty acidic at 5. Milk, slightly acidic, we'd say. above 7, close to neutral. Pure water at 25 degrees C would be pH 7, neutral. Blood is slightly basic. Sodium bicarbonate, slightly basic. Borax, slightly basic. Now we're getting more strongly basic, like milk of magnesia, pH 10, strongly basic. A lot of detergents are strongly basic. Aqueous ammonia is getting more basic, although aqueous ammonia we call weak base, partially. Bleach, as far as the solution goes, it'd be considered pretty basic. Bleach, sodium hydroxide. It also depends on the concentration. This is 1 molar. If you go to like 6 molar sodium hydroxide, it would be even more basic than this. So these are some examples of different things. pHs here. How do we measure pH? We measure pH with pH paper. This is pH indicator paper. It has different dyes incorporated in the paper that change color depending on pH. Or we use a pH meter like this. A pH meter has a little sensitive electrode here. And this is sensitive to the hydrogen ion concentration or hydronium ion concentration. There. This is a pH meter. Now, what about non-integer? Non-integer, we have to use this. So for example, the hydrogen ion concentration of a solution is 2.7 times 10 to the minus 6. That 2.7 screws things up because now it's between 10 to the minus 6 and 10 to the minus 5. You know, somewhere between 10 to the minus 6 and 10 to the minus 5. Because you know what 10 times 10 to the minus 6 is? 10 times 10 to the minus 6 is 10 to the minus 5. And so this is between 0 and 10. And so when we have this kind of number, then we have to use this equation here. We can use this equation for anything, but the pH is equal to the negative log of the H plus. And so we can't do it in our heads, we'll just plug it into the calculator. It's going to be the negative log of 2.7 times 10 to the minus 5. And so we just punch that in the calculator and see what it comes out to. I'll just do log of 2.7 times 10 to the minus 5. It's 2.7 times 10 to the minus 6. I misread it, sorry. 5.56. So it's between 5 and 6. As we predicted. 5.568. pH. Well, then the POHs, we just take 14 away from that. 9.43. And then the hydroxide ion concentration that's the power, so it's 10 to the minus 9.43 molar. We have to punch that in our calculator. And so we take the anti-log. .703 times 10 to the minus 10 molar. I'm not sure. We're probably not going to have these on there. I'm just showing you just for an example what you do here. Actually, sorry, the 10 to the minus 9. I screwed it up because I didn't fix it in my calculator. 8.43. 10 to the minus 9. I accidentally put in 5 here. This is supposed to be 6. 6. All right, so that's what you do when you have non-integers. You have to use the equations there, but it's pretty straightforward. We're just going to have integers on here, so it should be fairly straightforward to figure out pH based on the power. Okay, let's take a look at some more examples of pH with time. What's the pH of this one? Did we already do this? Yeah, okay, pH is 5. Get back to the chart. All right, so what's the pH of this one? So this would be 1 times 10 to the 0th. 10 to the 0th is 1. And so this is 10 to the 0th, the pH is 0. Here, this is 10 to the minus 10 to the minus 1. Therefore, the pH is 1. This is 10 to the minus 2 molar H plus. 10 to the minus 2 molar H plus, the pH is 2. When we get down to here, this is 10 to the minus 7 molar H plus. 10 to the minus 7 molar H plus is pH 7. And so all these pHs have higher H plus concentration than hydroxide. Once we pass the 7 boundary, then all those will have more hydroxide than hydrogen. And so if we go to the most basic solution, the most basic solution is here. Here the pH is, well, it's 10 to the minus 14 molar H plus. 10 to the minus 14 molar H plus means the pH is 14. Oh, actually, is the pH 14? Yeah, pH is 14, which means the pOH is 0. And if the pOH is 0, then it's 10 to the 0th molar OH minus. So it's going to have the most hydroxide. So that's that. And then one more thing. That's pH of solutions, and we're going to just look at reactions just briefly again. And so Bronsted acid-base reactions. Okay, pH happens when we have the hydrogen and the hydroxide in solution. But this is a different topic. This is when we're thinking about reacting acids and bases. So predicting acid-base reactions, we just want to transfer an H plus, and I gave you steps earlier, so I just want to review those steps. Basically, we're just going to use the chart. This is using the chart. Using the chart is this. We want to go from stronger acid to a weaker acid. Here. We can go from a stronger acid to a weaker acid by reacting with a stronger base. Here. We don't want to react it with a weaker base here, because if we react with a weaker base here, it will make it stronger acid. And so this is using the chart here to figure out what's going to react quickly. So when we have HF, we want to react it with a stronger base than fluoride, not a weaker base than fluoride. If we take HF and react it with a weaker base, like nitrite, HF plus nitrite would be the base. It takes the hydrogen. If nitrite takes the hydrogen, we form HNO2 and fluoride. And so when we compare this, HNO2 is a stronger acid, this is a weaker acid, so we're going from a weaker acid to a stronger acid. That's not favorable. what we need to do is we need to go HF and react with a stronger base, like this. So if we go HF and react with formate, this is called formate, then we're going to form formic acid. So HF plus formate, the hydrogen goes with formate, we form formic acid, and then we're going from stronger acid to weaker acid. And so HF reacts with all the bases that are stronger than fluoride. Let's list them. How about acetic acid? Acetic acid reacts with all the bases that are stronger than acetate. So for example, would acetic acid react with fluoride? No, because if acetic acid reacts with fluoride, we're going to form HF. HF is a stronger acid, so it's going backwards. Does that make sense? So this is just using the chart again for predicting acid-base reaction, peroxide acid-base reaction. And so what we'll do now is we'll just take a look at some additional problems. For this. Chapter 17. Let's take a look at number 19. What is the difference between a strong base and a weak base? Or what is the difference between a strong acid and a weak acid? The Bronsted-Lowry. What's that? There are different ways we can say this. Strong acids ionize or hydrolyze completely. And so strong acids produce a lot of hydronium. The same thing, weak bases like ammonia. Did weak base like ammonia produce a lot of hydroxide? No, it only produced like less than 0.1%. Right? Just a tiny bit. And so strong bases produce a lot of hydroxide, weak bases don't produce much. And just like strong acids and weak acids. So I showed you the example of a strong acid and a weak acid. Let me show you an example of a strong base and a weak base. So what is a strong base? A strong base would be something like sodium amide. Sodium amide is soluble, so we're going to get sodium ions and amide ions. And amide is a strong base. So soluble salts ionize completely. Well, amide, if there's water present, then the amide will hydrolyze water. So amide plus water forms what? What do bases do? Bases take hydrogen ions. Bases take hydrogen ions. So what's going to form? NH3. Now hydrogen ions, I screwed this up. It's NH2 minus. Hydrogen ions are positive, NH2 is minus. And so it's going to just form NH3 plus hydroxide. Now, we look at the base. This is the base, this is the acid. This is the, which is the base going backwards? Both ammonia and hydroxide are base, but they both aren't going to act as a base. Going backwards, which one's the base? Yeah, going backwards, who took the hydrogen? Did ammonia take a hydrogen or did hydroxide take a hydrogen? Hydroxide, because hydroxide took it to form H2O. That means ammonia lost one to form NH2. We went from 3 to 2. So this is the base, this is the acid. Now, which one's a stronger base? Which one's a stronger acid? So when we look at that, so when we look at this, we see that amide is a stronger base than hydroxide. And as far as acids go, water is a stronger acid than ammonium. And so we're going from stronger base and stronger acid to weaker acid and weaker base. And so we have driving force here. Driving force means lots of hydroxide should form. In other words, we have complete hydrolysis or complete ionization in this case. Although ionization doesn't make any sense, we have complete hydrolysis. Because we got driving force. That's a strong base. A weak base like ammonia, when ammonia and water react, so I have amide in water, it's going to form a very basic solution. The hydroxide ion concentration is going to be high and it's going to be very basic. When I have ammonia mixed with water, is it going to be as basic? No, it's not nearly going to be as basic because which way is the driving force on this? The driving force is backwards because we're going to form ammonium, which is a stronger acid, and hydroxide, which is a stronger base than what we start with. And so the driving force is this way. And so the difference between a strong base and a weak base is the amount of hydroxide that's produced. Strong base produces a lot of hydroxide. Weak base doesn't produce much hydroxide in water. Does that make sense? The difference between a strong acid and weak acid. Strong acids produce a lot of hydronium. Weak acids don't produce as much hydronium. That's what we have. Well, anyway, we're out of time, so let's stop there.